The first talk of the afternoon session is by Anton Khoroshkin, who is talking about the contracting a subgraph in a simple graph. Please.
Okay. Okay, so thank you for the invitation. And to be honest, the conference is called Representation Theory, Integrable Systems, and Beyond. So I will start from beyond story, and then the representation theory and integrable systems will come back late in the picture. So, and the most part of the talk will be about this beyond, but believe me that there is some connections which I hope those who will be able to follow till the end will got something from that. And for me, beyond mostly so far, what I will advertise for today is just to do some combinatorics. And this is a kind of approach to do some computations with graphs. So the graphs is story which is interesting for people from combinatorics, but of course I'm not, to be honest, I'm not a person from combinatorics, so that's why I will try to do some advertisement of some theory beyond this combinatorics. So, and the second announcement is this is mostly a joint work with my student D.Lyskov. So I will talk mostly about the first preprint, but he also wrote down under my supervision 2 other preprints, which a lot of theory behind this story is was worked out. And okay, so let me start. So what kind of combinatorics we do? So if you start from a simple graph, so simple simple means no loops and no double edges. So just vertices, and for each pair of vertices I know if they are connected by an edge or if they are not connected by an edge. And then you can do very simple things. So you can choose a subgraph. Simple, and also for some reasons it's better to talk about connected graphs. So then what you can do, you can look on a subgraph. What does it mean for me, subgraph? You look for the subset of vertices and look on the corresponding graph on all edges which are given here. So if this is graph gamma, I will denote, so this will be my subgraph G or subset of vertices. So this is in order to underline that I'm working with the subgraph coming from the bigger graph. I'm saying that I restrict gamma on the subset of vertices. Full subgraph, yes, all edges inside this story. And the second one is gamma divided by G. Contracted, what does it mean? So I contract all vertices in my graph, in my subgraph to one vertex, which I draw as a blow one, right? So I just take all this to one vertex. Then what may appear? I may appear, some double edges may appear. So a priori this should be here double edge, but double edges for me is the same as a one edge. So it's a well-defined operation. So if you start from a simple connected graph and the subset of vertices such that the corresponding subgraphs, this should be connected as well. Connected as well. So then you can define this operation. Very simple story. But then I want to use this operation in order to count some data about my graph. What kind of data can be covered out of this story? For example, what I can do, I can do with some enumerative data out of the graph of a graph. So what kind of data I can follow? So for example, I can look on the set of I don't know subtrees, spanning subtrees. subtree, or orientations, or also what I can do the Hamiltonian paths. Forests and whatever, and something else. So what is nice with this type of data? The nice is that they're well defined with respect to these two operations. What does it mean? So if I look for my graph, and I look, for example, for a Hamilton path, right? So Hamilton path is a path that starts from one vertex, goes, oops, this one is not, yeah, the path which goes through all vertices and exactly one time. So then, if I look on this path, then I know what is the image of this path on the subset of vertices. So in this case, this will be this story. And what is on the quotient? It is not always well defined, right? So if my path was going out of this story and coming back, then here it might be the problems. But in most of the cases, if it's well defined, then it's unique. So then for each Hamilton path here, I can say what is this one and what is this one. And the same story happens for all those combinatorial data. So for example, what orientation, so better to consider here acyclic orientations. This is more well defined to the story. So what is the acyclic orientation? So it means that I draw, make my set of vertices as a pole set, and then I can do this on the subgraph and on the quotient. The restriction that this is acyclic uniquely defines me what goes on. So these are some combinatorial data which you can assign first for each bigger graph, then for each subgraph, and for the quotient one. Okay, and what else nice with this operation is the following thing. So far I did it once, right? So I say that I have one graph and look on the restriction or on the quotient, but then I can iterate this procedure. So I can look for another subgraph. And another subset of vertices which either does not intersect with that one or belongs to this story. Then what I can do, I can iterate this procedure. So if this was G, this was G1, this was G2, then I can say what is gamma mod G and then mod G1. This will be just gamma G mod G1. This will be just one vertex. Oh, so G2. But look that this is the same, so I can put the brackets other way around. I can say that this is gamma mod G mod G1. So the meaning of this story is that so these all are well defined for subsets, subgraphs, and quotients, and the corresponding operations and the corresponding maps are associative. Now, what does it mean, associative? Associative means, once again, so that means that I can do it in any order. So if I start from a graph and draw the iteratively some subsets which I want to contract step by step, it doesn't matter in which order I do this contraction. And I use the word associative because this kind of structure which I get here is the structure which resembles the structure of associative algebra. So I want to mention you that, and this is one of the main advertisements of this talk, that you can look on all those data, you can think about them as an element of associative algebra. It will not be associative algebra, but it will be something similar. So something where you can do the computations like you get used to in the world of algebra. So in order to do this formally, let me give the definition. The formal definition. And this will be one of the main features of all those texts. So this is, I call it a contractad. This is coming from the word contraction plus operad, for those who are familiar with the word operads. In vector spaces. Maybe a contractad P is the following data. What type of data you have? So the first thing is that for each gamma, this is a kind of assignment, so gamma is a simple connected graph. So for each graph you have the vector space P of gamma, which will be now vector space. And then for any story like this, for any G inside gamma, which is also connected, I have a composition rule, which I write a little bit other way around compared to what I have here. So this will be, so from P of gamma restricted to G times P of gamma out by G to P of gamma. And so this is the data of my contractad. And now, such that the conditions on those properties. So the first thing is that, so this will be my G, gamma G, such that composition is associative. And equivalent with respect to equivariant with respect to the symmetries that you have on the graph. So for example, this graph does not have the automorphism, but a priori there are many graphs which have automorphism, and this map should survive this, should be compatible with this automorphism. Okay, so this is my definition, and now I claim that what I have here is an example of those in the following sense. Now what, so I erased the meaning, what does mean well defined for the contraction, meaning that I have, so the examples will be, the first one is spanning trees, so let me, is tree of gamma is just by definition, so I claim that I have for each those example, I have an example of for each those combinatorial data, I have an example of a contractad. What does it mean? So I have, for example, in this case, I want to define you the contractad of spanning subtrees in a graph. What it will be? So for each graph gamma, I need to assign a vector space. My vector space is a vector space with a basis given by spanning trees. Now, what are the operations? What is this maps which I want to define? So my map from P of gamma restricted times G of gamma mod out by G to meaning of gamma. So remember that what I defined before on the level of sets, I defined the map in the other way around. I defined for each graph, for each spanning tree of gamma, I defined the spanning tree of the quotient and the spanning tree on the subset. So you have to dualize this map. What that means, so if you have T1 from here, T2 from here, then the composition of those should be mapped to the sum of T from here such that T divided by T restricted on G is equal to T1 and T mod out by G is equal to T2. And you can do it for all those stories. It's absolutely the same thing. The only thing you have to dualize. Why I prefer dualizing? Because when you speak about the algebras, you have a map from the tensor product to itself. So that's why it's a bit more reasonable to think in this direction. Which map? This one? Yeah, first of all, there are quite many of those maps. Those maps are indexed by gamma and G. Yeah, that might happen. Yes, that might happen. This happened for this story. This happens for spanning trees. And one of the way to replace it, so if you think about the rooted one, then the story became a bit more better. What I mean I'm better? So let me say that that this structure, this definition of the contractad. So why I'm trying to deal with this story is that you can define the contractad given by generators and relations. So there is a well-defined notion of contractad given by generators and relations. Let me give you a couple of examples. And you are right that if you consider in the spanning trees, then the presentation in terms of generators and relations is a bit more complicated, but it's also possible. But for the other stories, it's a bit more simple. So the one which I can show on the board is, for example, the Hamiltonian path. So the example. So the contractad of Hamiltonian path is a contractad which is generated by one operation. So you have Ham generated on a graph with two vertices. So you can draw, so there's path in one direction and path in another direction. Right? So it's a two-dimensional space, and then subject to quadratic relations. What are the quadratic relations? So let me call it this one new, this one new opposite. So the quadratic relations, meaning that I want to use generators twice. So they are quadratic with respect to the generators. What does it mean? So how many graphs I can draw such that I can do this iteratively from these two operations using twice? So there are only two graphs. One is this, and another one is this one. And so for this graph, what I want to say? I want to say that if I draw the operation in this, and here I have here, and then I have here, this will be the same as the picture if I first drew here and second drew here. So that's maybe this. So this is the operation new with new. So this for this graph on three vertices, 1, 2, 3, I can get this. I have two or maybe three. So I have three different ways how to draw a subgraph, how to choose an edge with two vertices. And I'm claiming that either if I choose in this or I choose in this and draw this operation new here and new here, then I get the same. But if I draw one more relation, will be, this one is not interesting, but what is interesting here, so for this graph, I can do first go in this direction and second draw in this direction. So this is new and here new opposite. So this should be 0 because there is no such a Hamiltonian path such that on the restriction on the subgraph it gives me the direction in this, and on the quotient the direction will be the other way around. But anyway, so it's very simple game. So I'm claiming that this one is a quadratic, so subject to quadratic relations, which I don't want to write down on the board, but believe me, it's not so complicated. It's just everything done by hand. Sorry? No, this one is not monomial. This one is equal to this one. This is not a monomial relations. The relations are something like set theoretic. So you have either some monomial is equal to 0, or either the compositions is equal to the composition another way around. So something like that. What is more interesting is to do with this story and that one. But what I want to advertise you, and this is from where this theory comes out and where my hope that integrable systems will coming further, is the story. So one more coming from another example, which is the example very known for people from topology, which is called the, and so this will be generalized configuration spaces. What do I mean? So I want to assign for a graph gamma a configuration space gamma of x, which is given by, so this is the collection of elements in my x. So this will be x1, xn, where n is the number of vertices, such that I take off those diagonals for which I have an edge in the graph, minus unions of xi equal xj if ij is inside E of gamma. So if gamma is just a complete graph, then you get just the ordinary configuration space. But it's also interesting to deal with not only with ordinary one, but with those one. So I claim that this is an example of a contractad. So it's not obvious what to do when you look on the subset or look on the quotient set. So the one which in algebraic topology it will be called little disks contractad. So my spaces, I want to modify a little bit my space configuration space of points by replacing the points with the smaller disks. So I apply to this conf gamma. First of all, I consider X to be just the flat space, or maybe even a disk, d-dimensional. And second, by this I mean I draw the very famous picture, which is from where these little disks comes out. I draw not the points, but I draw the balls inside the unit ball. But I allow those balls intersect if I have an edge here. So this is collection of unit balls. I draw the cubes or balls or cube. On the topological level, it doesn't really matter. Such that di with dj, the intersection is 0 if ij is an edge in your graph. Then what you can do in this, when you enlarge those pictures, then what you can do, you can put, collect the stories. So if I have something for the subgraph and something for the quotient one, I claim that I can draw the bigger one just substituting one graph to another. So I just, if I draw here a bit smaller configuration, and I erase the latter one, then you just get, so this conf of conf gamma restricted to G of D times conf, not G, map to conf gamma of D by just substitution, making it small and putting one inside the respective story into this vertex, which, so you have the configuration for this graph, you have configuration for that graph, and then you want to put the upper one, you want to put this configuration into this point. So I mean you put it into this ball and then erase the bound. Okay, so this is a very nice example, which is really helpful for those who is working with the configuration spaces, because it allows you to. The intersection should be empty. Yes. If they are not connected by an edge, the intersection might be empty, might be not. The only restriction is if you have an edge, then it's not allowed to intersect. Okay, so so one more thing for this story is these are the topological spaces, and I give you the definition only for vector spaces. So in order to come back to the category of vector spaces, you have to make some functor, the functor which the monoidal functor. So what else you have to do? So you have to take the homology of those configuration spaces. And now one more claim of this type of story is that this is the theorem that the homology of this conf of RD is a contractad that generated by the homology of for 2 points. For the graph with 2 points, it's very simple. It's just you have to the configuration space of 2 points inside the d-dimensional. This is just a sphere. d minus 1. So you have homology. So you have mu which of inside of homological degree 0 and another one in homological degree d minus 1. And so the most interesting case when d equals 2, and then this will be of degree 1, and it's this is what people in opera theory likes very well. And so this is generated by binary operations. Now subject to quadratic relations. the quadratic relations once again. So you have to define the quadratic relations for graph with 3 vertices. So there are some relations which are given for this graph and another type of relations which are given for this one. So the relations which you get for this one is very well known for the people from opera theories. It's saying that what? So you have the mu. So this corresponds to the operatic relations. So I don't want to go to the definition of the operad, but this is roughly speaking all this story for assigned to the complete graph. But what does it mean? So you have, so the mu is a commutative associative product. This means that if you draw the picture like this and then like this, so you can draw 3 pictures of this kind. You can do like this, like this. So mu remembers just the number of connected components because this is just H0. So they all should be the same because all those spaces are for when d is greater than 1 is just connected spaces. So this is kind of associativity of this commutative product. And this one mu is what in opera theory is called the Lie bracket, because the relations which you get for those one, for the another one, is just the dual to this one. So the linear dual set of relations, meaning that for mu you have the sum of those should be 0. So that the space which is orthogonal. And the same type of relations you can write down for this graph as well. Let me draw it. So here you have now 2 graphs. So this one should be equal to this one. And this both for this one and both for this one up to some signs. So there are some sign conventions which you have to follow, but this is not a big problem. And the sign should depend on D. Anyway, so, and the last thing is the compatibility of mu and nu. And roughly speaking, so plus Leibniz identity. And Leibniz identity tells you the following. So if you have, if you have mu inside and mu outside, then you can write them other way around. You can write mu inside and mu outside, plus maybe the term with the other story. So, but anyway, so the key point is that whenever you have mu inside nu, then you can put it out. So the claim is that it's everything is by hand, and you check it on very simple set of graphs, on just with 2 vertices and with 3 vertices, which are all under control, and then out of this story you can say what you get for the bigger graph, for a high graph, for arbitrary huge graph. What does it mean you can say? It means that you have a structure which is given by generators and relations. And now the next feature of this story comes into the game. But so now I want to explain you what does it mean to say something about the arbitrary graph. Because so far I do more or less nothing. I do some simple computations for on 2 and 3 vertices. Now, if you go further, so next Yeah. Sorry? Yeah. Yes. Sorry. It was written. So this one, configuration space, is a contractad generated by this one, subject to quadratic relations. So this should be everything like this. So you have here generators, here relations. Yes. If you look on two balls, 1 and 2, so then you can put, first you can fix this one into the 0, because this is the homotopy, so you can move it everywhere. So this one is fixed to be in the 0 line, in the 0 point, in the coordinate, and that one should not coincide with this one. You can say that the length with respect to between this and this should be 1. So I claim that this one is, that this configuration space of 2 points in RD is not the same as this one, but is homotopically equivalent. And so I show you two homotopies. By the first homotopy you fix the origin, and by the second homotopy you fix the length. Or you can say that if you mod out by R plus times RD, these are the shifts, and these are so this is the contractible group, and this one is, this quotient is SD minus 1. Okay? Great. So now, what kind of data you can get out of this story? So I will not explain you all the data which you can get from this definition, but I mentioned this as a theorem without explaining what is inside, is that there exists a theory of Grobner basis for contractads. So roughly speaking, this means that there is one can explain what is a monomial what is a monomial, what is a partial order, what is a total order on monomials, or maybe order. So you can, for each expression, you can say what is a leading monomial of this expression. And this is, so in order to explain the details, I have to explain you the theory of Grobner base, which I don't want to do right now. But the output of the story is, there is an algorithm. So if one was able to find the Grobner basis, of P, then there is an algorithm to find the basis in P of gamma for each gamma, and do it inductively using this type of contractions. So this algorithm might be complicated, but still you can get some some output. And the output of this story, which I want to advertise right now, because it's really not so simple how to find the Grobner basis, you have to check something. It's some check, but for those operas which was written here, if we were able to explain that they are given by quadratic relations, then it's not so hard to show that they are that they admit a quadratic Grobner basis. But one more application, and now I'm coming to. Yes. Everything. So all the theory of Grobner basis which you get used to for associative algebras can be extracted here. The problem is that the structure of monomials is much more complicated compared to what you get used to. Yes. And now some corollary. Which you can get out of the story is that we can do the computations of generating series. And let me define one of the main generating series for collection of graphs. Now, the main series which I want to advertise right now will be just complete multipartite graphs, which is called K lambda. Lambda is a partition. So this is the place where the representation theory coming out. So K lambda is a graph which I have lambda 1 points here, lambda 2 points here, and so on. And you have edges between different groups. You have all edges between different groups, but inside each group you do not have an edge. So then I can write down the following generating series y of p, which is given on one variable z and x1 and so on, and which is given by the sum greater than 0 dimension of p k lambda, and I add a group of vertices with one element, and then I multiply it by z to the power n factorial times m lambda divided by lambda factorial, where m lambda is just the symmetrization of x1 1 factorial, x2 lambda 2 factorial, and so on. So you can write down this series. So practically, the only thing you need is just for z equals 0. But it's important to have this extra variable z. And now, out of this story, let me mention a couple of corollaries. So, for example, for Hamilton path, so y of Hamilton, even without z, it's also interesting, will be just, and it's a bit simpler, sum 1 plus sum pn. Let me check formulas. Sum Pn divided by n. Oops, this one. Yes, yes. Yeah, without weights. N minus 1, Pn. Where Pn is just the Newton sum xi to the power n. And y, let me write another one, which is also configurations, will be 1 plus sum Pn divided by n q, where q counts the homological degree. And maybe one more for acyclic rotations. Sorry? N factorial. Sorry? No. This is about the configuration space. Yes, for configurations with respect to, so these formals are written for configurations of points inside the C. Configurations, once again, for complete multipartite graph. So this is. So a priori, this is known to be a chromatic polynomial. But if you try to count the chromatic polynomial of a complete multipartite graph for arbitrary lambdas, I never seen it in the literature. So this is the first formula which you can get. So this is the theorem of myself and D.Lyskov. And there are some more examples from integrable systems related to the moduli spaces of curves, which I do not have time to explain right now. Okay.
Thank you, Anton. Any more questions or comments? Okay, we had several questions. There is one.
Very small question. So this probably makes sense in the generality of matroids, right? All of this.
Sorry?
All of this probably makes sense in the generality of matroids, right? Well,
Yes. The story is, for me, I have been thinking about the graphs because my key example was this configuration spaces and the Deligne-Mumford compactification of the moduli space of curves, where you can also write down a lot of information out of this story. But you are right that you can do some generalizations for another combinatorial things like matroids. But there is a problem. So there is a theory of Grobner basis, but it's really quite often it's complicated to show that some operand is quadratic, is generated by binary operations and quadratic relations. This is some task in all this. And whenever, as much a complicated object you consider, then it's beginning more complicated. So for metroids, it's not always true.
Thanks.
Is it clear what is connection to representation theory and like how do you prove these character formulas?
These formulas are proven using the homological algebra around the story. So if you have the theory of Grobner basis, you have the theory of Kazul duality, and there's this. You can write down the functional equations on the contractad and its Kazul dual, and all these formulas are some computations with those series, with the starting from writing down the functional equation for for a simple operator and for simple contractad and for its scheduled dual, you get some series, and it's quite nice. I strongly recommend to look on those papers if you're interested.
Any more questions? Then let us thank Anton again